Welcome students for this P block session. This is a very scoring topic, but most of the topics are removed from this chapter in the recent syllabus. If you see the new NCERT textbook, you don't even find the name of this chapter also. So you have to go to the old NCERT textbook to read the contents of this chapter within the syllabus. And what is there actually the syllabus from this chapter? Actually, it is from group 13 to group 18. In these topics, you have to only focus on the general trends in each group and what are the anomalous properties of the first element in this group, that is second period element. All rest, that is compounds of these chapters of these groups are completely removed. Now we will see questions related to the general trends and the anomalous behavior of the element in those respective groups. Let's start. The correct order of atomic radii in group 13 elements is, see, in group 13 elements, generally in group, atomic size increases down, but it is not so in every group. There are some anomalies. In group 13, if you see boron is the smallest size. When you go to the aluminum, it increases. And from aluminum to gallium, we expect size should increase, but here, due to the poor shielding effect of d orbitals, size decreases here. Then after gallium, indium, till indium it increases, and after indium to thallium, again there is a increment is there. But the increment here from indium to thallium is very small, again due to the poor shielding effect of F electrons in thallium. There is an increment, but the increment is not as high as our expectation. It is small increment, but at least it is increasing. So, if you see the trend, boron to thallium, it is increasing, but there is an exceptional case for the gallium. Gallium is decreasing here. It is below than the neighbors. So, highest is thallium, then comes indium, but here gallium is given, which is wrong. So, but if you go to the option D, thallium, then indium, after that aluminum, then after aluminum, gallium is coming into picture. Then least one is boron. So this is the right option. Now see the next question. The stability of +1 oxidation state among aluminum, gallium, indium and thallium increases in what sequence? See, among these elements of this group, boron, aluminum, gallium, indium and thallium, we see two oxidation states. One is +3 and +1. As you go down the group, stability of +3 oxidation state decreases. Stability decreases. That means boron is more stable in +3 state, highly stable, and whereas thallium is less stable in the +3 state. But whereas if you see the +1 oxidation state, it is reverse. Boron is least stable in +1 state. It is so least stable, it won't even exist also. Thallium mainly exists in the +1 state. It is highly stable in that state. So, why this is happening? Because if you see boron configuration 2s2 2p1. Now, it is easy to excite the electrons from the 2s to 2p because the energy gap between s and p is very small. It is easy to excite. Creating 3 unpaired electrons, therefore it is easy to form 3 bonds and exhibiting the +3 state. But as you go down the group, the gap between Ns and Np increases. If you go to thallium, here valence shell is 6 shell and there is a large gap between 6s and 6p. There are other orbitals coming in between them also. So the energy gap between 6s and 6p is more, so it is difficult to excite electron into 6p. So if it is difficult to excite the electron, then it is difficult to create 3 unpaired electrons to exhibit the +3 state. That's why thallium mainly exists in the +1 oxidation state. It is highly stable in that state. So if you see what is the correct option, thallium +1 stability is more, after that indium, gallium, then aluminum. So this is the right option. Which one of the following elements is unable to form MF6-3? That means octahedral. Around M there are 6 bonds are there with fluorine. They are asking which is difficult to form. Now if you look at the boron valence shell is second shell. So it has only 2s and 2p subshells. There is no 2d. Since there is no 2d, it cannot exceed the octet configuration, or it cannot exceed more than 4 covalent bonds. So therefore 6 covalent bonds around the boron is not possible. Hence C is the right option, because they are asking unable to form. Look at this question. The tendency of BF3, BCl3, BBr3 to behave as Lewis acid decreases in the sequence. See, in these boron halides, there is a back bonding. If you look at the BF3, the vacant orbital in the boron, vacant p orbital, and the lone pair containing p orbital in the fluorine, there is a lateral overlap. So because of this lateral overlap, boron is partially getting the electrons from the fluorine. This is called back bonding. We represent like this: B, F, and there is a pi bond, and both electrons are donated from the fluorine to the boron, and this is called back bonding. Now because of the back bonding, the electron deficiency of boron is partially satisfied because it is getting electrons from the neighboring element. And similarly it happens for the BCl3 also, BBr3 also. But in case of BF3, the overlap is between 2p orbital of boron and 2p orbital of fluorine. So when the size difference between the lateral overlapping orbitals is small, then the overlap is more effective. So 2p overlap is very good. Whereas when you go to BCl3, boron's 2p orbital overlap with the chlorine's 3p orbital. So the overlap is not that effective like in case of BF3. And if you go to BBr3, 2p and 4p is even less effective there. So therefore, boron is getting electrons very effectively from fluorine and less effective from chlorine and less effective from bromine. So therefore, here boron deficiency, electron deficiency is mostly satisfied from the neighboring element fluorine, because it is getting electrons within the neighbor from the neighbor only within the compound. So electron deficiency is so much satisfied here. It does not readily accept the electrons from the outside compound. If outside some acid, Lewis base is there, which comes to donate electrons to the boron, it is not so ready to accept those electrons, because it is already getting the electrons from inside, from the fluorine element. Therefore, BF3 is weak Lewis acid. It does not readily accept electrons from the Lewis base. Therefore, if you see BF3 is in the last here in the second option. BF3 is the weak, then comes BCl3, then comes BBr3. BBr3 is the strong Lewis acid. See in this question, which of the following is incorrect? In such questions, read all the 4 statements, then only decide the answer. Do not just read the first statement and decide the answer. Sometimes after reading 2 or 3 statements, you may change your decision also. That's why read all the statements, then see which is correct or incorrect. SnF4 is ionic in nature. Yes, due to the large electronegativity difference between tin and fluorine, it is ionic in nature. If you read NCERT, it is mentioned clearly. SnF4, PbF4, they are ionic compounds, not covalent compounds. And PbF4, they are saying covalent. So this is wrong statement. And SaCl4 is easily hydrolyzed. Yes, in SaCl4, the vacant d orbitals present in the silicon easily accepts the electron pair from the water and undergo the hydrolysis. Therefore, SaCl4 easily get hydrolyzed. Next, GeX4, germanium. GeX4 is more stable than GeX2. Germanium. Germanium belongs to carbon family. And carbon family, carbon, silicon, germanium, tin, lead. So here +4 state and +2 state. There are 2 states it will exhibit. And when it comes to germanium and tin, +4 state is more stable than +2 state, whereas in case of lead, +4 state is less stable than +2 state due to the inert pair effect. So they are saying germanium, here germanium is in +4 state and that is more stable than the germanium in the +2 state. And it happens with the tin also, but in case of lead, reverse. Reverse means lead plus 2 state is more stable than the plus 4 state. So if you see among these 4 options, second option is the incorrect one. Which of the following species is not stable? See, if you see silicon, around silicon, there are 6 chlorines are there. It is difficult to accommodate the large sized chlorine atoms around the silicon. Fluorines are okay. Fluorines are small size. 6 fluorines can fit around the silicon. But chlorines, which are bigger in size, it is difficult to fit around the silicon. There is a repulsion between them, because when they are bigger in size, they will be very close, crowded. So when they are very close and crowded, the repulsion between them makes the overall molecule unstable. That's why SiCl6 minus 2 is not stable to exist. It is also mentioned in the NCERT. And whereas other cases, silicon, germanium, tin, they are bigger in size, there is no problem to accommodate the large sized chlorine atoms there. Next, it is because of inability of NS2 electrons of the valence shell to participate in bonding that. See, if you look at these options, all belongs to this group 14. In group 14, they are saying the inability of NS2 electrons to participate in bonding, which is called actually inert pair effect they are talking about. Because of inert pair effect, which option is correct, they are asking. See, tin, carbon, silicon, germanium, tin and lead. Now in this group, 2 oxidation states we see, plus 4 and plus 2 state. Now in case of germanium and tin, plus 4 state is more stable than plus 2 state, whereas lead case, plus 4 state is less stable than plus 2 state. Now here, since plus 2 is more stable than plus 4 easily converts into plus 2 state. Lead plus 4 compound easily converts into plus 2 state. That means it easily undergoes the reduction, thereby acts as good oxidizing agent. So Pb plus 4 is a good oxidizing agent. Good oxidizing agent means good oxidizing power. Good oxidizing power to oxidize the other one. Next, in case of tin, Sn plus 2 is less stable. Therefore, Sn plus 2 easily converts into Sn plus 4. Means Sn plus 2 easily get oxidized to Sn plus 4. Therefore, it acts as a good reducing agent. So, Sn plus 2 is a good reducing agent. That means it is good at reducing the other one. So, if you look at the options, in the fourth option, Sn plus 2 is reducing. Reducing means what? Don't think that it is undergoing reduction. Sn plus 2 is reducing means it is reducing the other one. So, it is acting as a reducing agent. That is what it means. So, Sn plus 2 is reducing, whereas Pb plus 4 is a oxidizing in nature. So, this is the right option for this. Now, see this question. Which of the following oxidation states are the most characteristic of lead and tin respectively? So, in case of lead, among plus 4 plus 2 is more stable, whereas in case of tin, plus 4 is more stable than plus 2. Therefore, plus 2 and plus 4, these are the most characteristic for these elements. Which of the following does not show electrical conduction? That means they are asking which does not conduct electricity. See, among graphite and diamond, graphite has a hexagonal layer like structure. So, around each carbon, there are 3 surrounding carbons exist in graphite around each carbon. And if you see, carbon has 4 valence electrons. Among these 4, 3 are participating in the sigma bond with the neighboring carbons. 1 is remaining. Because of this remaining unpaired electrons, in the each carbon, it is a very good conductor of electricity, graphite. But when you go to diamond, around each carbon of diamond, there are 4 other carbons. So, all 4 valence electrons are participating in bonding. There are no unpaired electrons present in any carbon. Therefore, it is a bad conductor of electricity or insulator. Therefore, which does not show electrical conduction, diamond does not conduct electricity, graphite conducts fine, potassium and sodium, they are metals, and we know that metals are very good conductors of electricity, so they also conduct. So, the only one which does not conduct is diamond. Which of the following does not act as Lewis acid? See, BF3. BF3 acts as Lewis acid because boron has vacant orbital to gain the electrons. So, if Lewis base is coming towards it to donate electrons, boron is ready to take. So, it is a Lewis acid, but they are asking does not act as Lewis acid. So, this is not the answer. SnCl4. This also takes up the electrons because tin has a vacant orbitals inside. So, vacant d orbitals are there, it can also accept. But carbon, in CCl4, carbon has around it there are 4 covalent bonds, and carbon belongs to second period. It can form only 4 bonds and all 4 bonds are satisfied here. There are no vacant d orbitals present in carbon to accept the electrons into it. Therefore, CCl4 cannot act as Lewis acid. That is why actually even CCl4 cannot undergo hydrolysis also because of this reason. When water molecules comes to donate electrons, CCl4 cannot accept because there are no vacant d orbitals. So, it is not Lewis acid. SF4, again sulfur has vacant d orbitals present, it can accept the electrons and it is again Lewis acid. So, for answer for this question is CCl4. In which of the following compounds nitrogen exhibits highest oxidation state? See, first one, if you see, hydrogen will be having +1 state generally when it is combined with the non-metals. Nitrogen is a non-metal, so hydrogen combined with it has a +1 state. Now, if hydrogen is +1 and nitrogen, let's say X, we need to find this X. Like that, in every option we have to find and see which one has the lowest, highest value. So, 2 nitrogens, 2 into X plus 4 into +1 is equal to overall charge of the compound, which is 0. Sum of all oxidation states should be equal to its overall charge. Here overall charge is 0. Now, from this you will get X is equal to -2. Likewise, you will find for others also. So, here X plus 3 into +1 is equal to 0. So, X is equal to -3. Here is equal to 0, you will get X is equal to -1/3. Here again oxygen -2, hydrogen +1. So, 1 nitrogen is present and overall how many hydrogens? 3 hydrogens are present. So, let's take 3 hydrogens into +1 and oxygen, 1 oxygen is present, it has a -2 oxidation state. So, 3 minus 2, 1, if that 1 goes to that side, -1. Now, if you look at this, the highest oxidation state they are asking, and when you compare the negative numbers, the smallest magnitude will be the overall highest value. So, if you compare all are negative, so just look at the magnitude, which is the smallest magnitude, 1/3. Therefore, -1/3 is the highest value. So, this is the right answer. Next question. Nitrogen forms N2 but phosphorus does not form P2. However, it forms P4. Reason is what? See, in case of N2, there are pi, because 2p overlap is better to form a pi bond. But whereas in case of phosphorus and others in this group, as size increases, lateral overlap is so less effective that they is not stable to form. Therefore, here if you see, in phosphorus case, why it is not forming P2? Because p-pi bond is weak in case of phosphorus. In case of nitrogen, 2p overlap is very good, therefore pi bond is strong there because size is small for the 2p. Whereas in phosphorus, 3p overlap has to take place and large size orbitals cannot effectively overlap, that's why weak bond. Next, which of the following oxides is most acidic? Now see, suppose I am taking nitrogen oxides. For example, if I take an N2O5, nitrogen, P2O5 like this, I am taking different oxides of same oxidation state. Within the group I am taking N2O5. If you see nitrogen plus 5 state, phosphorus plus 5, arsenic plus 5, all same oxidation state. But in a group I am taking those elements, nitrogen, phosphorus, arsenic likewise. Then the smaller the size, the smaller the size of the central atom, the better the acidic nature of that oxide. Okay. So N2O5, nitrogen is smaller size, and as you go down the group size increases, therefore acidic character decreases here. But suppose if they give oxides like this, N2O3, N2O5. Now see here, both are nitrogens only here. But what is the difference? Here oxidation states are different. In N2O3 nitrogen plus 3, in N2O5 plus 5 state. Now in that case, the higher the oxidation state of the central element, the higher the acidic nature. Therefore here acidic nature is low for N2O3, high for N2O5. Okay. Now if you look at this question, here the central element is varying, and along the group there is varying. Nitrogen, phosphorus, arsenic, antimony. In a group it is varying. Therefore, the smaller the size, the higher the acidic nature. So N2O5 is the better acid among them. Among the following oxides, the lowest acidic is. Now if you see here, these both belong to phosphorus oxides, these both arsenic. And in a group we know as size increases, acidic nature decreases. Therefore, lowest acidic nature will be for arsenic oxides as compared to phosphorus. Now, in these arsenic oxides there are again two compounds. How to decide? See here, in the first case arsenic is in plus 3 state, in second case arsenic is in plus 5 state. So, and we know that as oxidation state increases for a given element, acidic nature increases. Therefore, As4O10 is more acidic, As4O6 is less acidic. We want that only, less acidic. So, this is the answer for this. Which of the following has the highest dipole moment? See, if you look at these compounds, all are the hydrates of group 15. This is the ammonia. Now, in NH bond, since nitrogen is more electronegative than hydrogen, the dipole moment, the direction of dipole moment is something like this. Similarly, here also and here also. So, and these three NH bonds dipole moment is like this. And lone pair also has a dipole moment from the and it has a direction from the nucleus towards that electron pair. So, therefore, this is the direction of the lone pair's dipole moment. Now, these all will get added up, and that is the net dipole moment. And what they are saying in the question, highest dipole moment we have to decide. Now, among the bonds, NH bond, pH bond, etc., nitrogen is more electronegative out of all the elements in this group. Therefore, the bond, when the electronegativity difference is high, the dipole moment will be high. Therefore, in NH3, the dipole moment of each bond is high. Therefore, overall dipole moment of the molecule also will be high. This is the answer. Next question. The basic character of hydrates of the fifth group elements decreases in the order. See, basic character we have to see. And NH3. And all these elements have a lone pair on the central atom, so they can act as a donor and therefore act as bases. They are asking which is the better one, which is the weaker one. Now see, if you look at the nitrogen has a smaller size than phosphorus. So smaller size, the lone pair is distributed on the smaller size element. And if you have, suppose if you take a ball and put a charge Q on it, the smaller the size of the ball, the smaller the surface area, the better the attractive force. Suppose if you take a big sphere, large surface area, and if you put the same charge upon it, now the charge density, charge per unit area will be less, so attractive force also will be less. So, the smaller the size, the greater the charge density and greater the attractive force. Hence, nitrogen, which is smaller in size, the lone pair will have a better attractive force, and therefore it attracts the Lewis acid better, and therefore it acts as a Lewis base better. Therefore, NH3 is the highly basic here, followed by phosphorus, which is the next in size, then comes arsenic, then comes antimony. So this is the right answer for this. Which of the following fluorides does not exist? See, if you look at this, first one, nitrogen has around it, there are 5 bonds, which is not possible because nitrogen is a second period element which cannot exceed more than 4 bonds because it cannot exceed more than octet. So therefore, 5 bonds is not possible for the nitrogen because there is no vacant d orbitals in the second shell, that's why. In other cases, vacant d orbitals are present, they can exist. Which one has the lowest boiling point? See, if you look at this boiling point order of the hydrates of group 15, pH3, arsenic, ammonia and antimony. See, if you just forget about ammonia for the time being, the other 3 if you see, phosphorus, arsenic and antimony, as the size increases, the intermolecular van der Waals forces increases. Therefore, boiling point, when intermolecular forces are strong, it is difficult to separate in the boiling process. Therefore, boiling point is increasing like this. Now, with the same explanation, we will expect that ammonia, nitrogen is smaller in size, so it should be in the last, but instead it is occupying the 3rd place. Why? Because in NH3, between the molecules, there is a hydrogen bonding, which is a stronger force. That's why, because of that, it is occupying the 3rd place. What place it occupies because of the strong hydrogen bond, that we cannot decide theoretically. That is purely experimental. We can explain why it is not occupying the last place, instead it is occupying 3rd place. We can explain it with the hydrogen bonding, but we cannot predict the order. We have to know the order. So remember this order. In such questions, it will help. So, lowest boiling point is for which one? Phosphine, pH 3. Each of the following is true for white and red phosphorus except that they. See, white phosphorus and red phosphorus both are covalent compounds, not ionic. So, we expect they dissolve better in the non-polar solvents like carbon disulfide. But white phosphorus dissolves better in the carbon disulfide, non-polar solvent, but not the red phosphorus, because red phosphorus is a polymer. So, because of polymeric nature, it easily comes down and precipitates even though non-polar solvent we use. So, both are soluble is wrong, only white phosphorus is soluble. And other cases all works for white and red, both will get oxidized in air, both will form phosphorus oxides when you combust in air, and both have same kind of atoms, that is only phosphorus only, and both can be, one can be converted into other, white to red phosphorus is possible to convert. Therefore, these 3 are correct options. First one is only the wrong option. Which of the following molecules is a paramagnetic? Paramagnetic questions, how to see? You have to look for the unpaired electrons. Now, there are few substances I will mention, few compounds, remember them. See, NO and NO2, ClO2, ClO3. See, among this group 13 to group 18, if you see, few oxides which are paramagnetic in nature. Okay, those are these 4. NO, NO2, there are one unpaired electron in here, and similarly unpaired electrons are present in the ClO2 and ClO3 also. Remember this, these are paramagnetic, rest all oxides are diamagnetic. So, paramagnetic, here NO2 is there, so that is the paramagnetic. Which of the following is arranged in the increasing order of enthalpy of vaporization? Now see, delta H vaporization means what? Energy required to convert liquid to vapor. 1 mole of liquid to 1 mole of vapor, how much energy is required? That is this enthalpy. Now, suppose if intermolecular forces are strong, then it is difficult to vaporize, more energy is required. In other words, boiling point also will be more for that. So, in other words, whichever is having the high boiling point, that will require the high energy to vaporize. Enthalpy of vaporization will be more. So, I would say delta H vaporization proportional to the boiling point. So we know the boiling point order already. pH3, ASH3, NH3 and antimony hydride, SbH3. So this is the boiling point order, therefore vaporization order also. So increasing order they are saying. So lowest is pH3, then comes ASH3, then comes NH3. This is the right answer. That's it. These are some important models, questions on the P block, group 13 and group 14 chapters. Now read the NCERT properly, the general trends as well as the anomalous properties of the first element in the respective groups. I hope this questions, explanation of these questions will be helping you. All the best. Thank you.